Hello everyone, welcome back to Z Physics. Today we're going to be revising the motion topic. I'm going to be following the OCR Physics A specification. However, as always, the physics is applicable to all exam boards. Now, if you guys are looking for projectile motion in particular, I have a whole separate video for this, so please have a look at the link in the description. Okay, well, let's get started revising. The first little topic that I would like to revise is the difference between distance and displacement. Now remember, distance is a scalar and displacement is a vector. Now what do I mean by this? The distance that a car will travel from A to B will actually be defined as the total length of this path over here between the 2 points. In other words, if you can think, let's say, of the mile meter inside of the car, it will be the total distance the car has traveled in miles, for instance, or in meters between points A and B. Now the displacement, on the other hand, is defined as the distance in a particular direction. So for instance, the overall distance between A and B will be given by the length of the path between them. Let's see if we can draw this relatively accurately. So the displacement will be given by the length of this red line over here, whereas the distance will be the length of this path. Now with that in mind, we can also define two further quantities. One of those will be the average speed, which is a scalar quantity, and this will be equal to the total distance. So let's move that here, the total distance divided by the total time. Now the total distance is just this path over here from A to B. We could also define our average velocity. So let's just write that down. Our average velocity will be equal to the total displacement now, divided by the total time. Now for that, for the average velocity, we're going to use this length over here. So let me just highlight that in red, because it's very important not to confuse the two. Average speed is a scalar quantity, so I'm just going to write that down here, that this is a scalar, whereas the average velocity is a vector quantity because displacement is a vector. One more thing that I would like to mention now that we're revising velocity is that if we end up back in the original position, so let's say that this car starts at a point, then does a circle, and then goes back to its original point, then the total displacement for this path will actually be 0. So the displacement in this case is equal to 0 because the distance in that direction, well, from the original position is actually 0. So in this case, the displacement is 0. Now, talking about average velocity, we also need to introduce the concept of instantaneous velocity. Now this is just our velocity at a particular point in time. So for instance, when this car over here is traveling, it's not always going to have a velocity equal to, let's say, I don't know, 50 kilometers an hour. It will be varying. So the car will be slowing down before a corner, they will be accelerating out of the corner, they will be slowing down again, accelerating, etc. So in the real world, the speed tends to vary for most things. So the way we introduce that in physics is with the concept of instantaneous velocity, which is the velocity at a particular point in time. You can kind of think of it as the velocity being the rate of change of displacement, so delta S over delta T. When this interval delta T becomes really small, then we are actually finding the velocity at a particular point in time. If we have a graph though, And let's say that the graph did not have a constant gradient. So you can see that this graph here is varying, and let's say that the speed at point 1 will actually be different than the speed at point 2. So if that's the case, we can find the instantaneous velocity by drawing the tangent. So this is really important. It's quite often a past paper question, so let me just put that in a box. Instantaneous velocity is the gradient of the tangent in a displacement time graph. So for instance, if I wanted to find the gradient at, let's say, point 1, so what I would do is I would draw my tangent, and I would draw a nice large line across here, and then I would use the rule for finding the gradient to figure out my instantaneous velocity at point 1. So v, in this case, let's call it at point 1, will be equal to delta y over delta x, where delta y, of course, will be the change in the y coordinate, and delta x will be the change in the x coordinate. So that will just be delta d divided by delta t. If I wanted to find the speed at point 2, I would of course then draw the tangent at point 2. I have a very detailed video on instantaneous velocity, so if you want to look at some worked examples, please check out this video, which is in my more detailed motion playlist. Now let's revise some important definitions. First of all, speed is defined as the rate of change of distance, whereas velocity is defined as the rate of change of displacement. Typically in A-level physics, you will come across the symbol S for displacement, and the velocity v is the rate of change of displacement, so delta S divided by delta t, whereas this here is the symbol for displacement. So because of this, the gradient in a displacement time graph, change in displacement over change in time, is actually our velocity. So this is equal to our velocity. Via the exactly same logic, the gradient in a distance time graph is your speed. So the gradient here is equal to the speed. Okay, on to acceleration next. This is a very similar concept to the concept of velocity, which was the rate of change of displacement. Acceleration, on the other hand, is defined as the rate of change of velocity. Mathematically, we write this down as a is equal to delta v, which is the velocity, divided by delta t. The units for acceleration, remember, are meters per second squared. Another way of thinking about this is that the velocity is measured in meters per second. Then we divide this by seconds again, which is equal to meters per second squared. Now, in a v against t graph, so that's a velocity time graph, acceleration is the gradient. So if I wanted to find the gradient of this line, I would do a large gradient triangle, and then I would calculate my delta y, then I'll calculate my delta x, change in y, which is v, divided by change in x, which is t. This is my acceleration. If I want to find my instantaneous acceleration, so for instance, if the velocity time graph was not a straight line, what I would need to do is look for the tangent of the gradient. So I'll pick a point, so let's say I pick a point here, and then I'll draw the tangent, and then I'll find the gradient of that tangent. So it's really important, the instantaneous acceleration is the gradient of the tangent. Yet another really important fact that we need to mention is that the area underneath a velocity time graph is the displacement. So for instance, the total displacement in this situation will be given by the area underneath this graph, like so. And if we're interested in the displacement, let's say from time, should we just write in some number? Let's say between 0 and let's say that this here is 5 seconds, then the total displacement will be given by the area, which of course will be this area over here. But yeah, once again, the area under a velocity time graph is the displacement. Okay, now on to the equations of motion next. First off, just a little disclaimer that these are valid only for constant acceleration. We have a list of 4 equations that were given in A Level Physics that you don't need to remember them. They will be given in your formula booklet. However, we're going to be using them so much that they'll probably become second nature and you will remember them. Now, in those equations, V is always defined as the final velocity, U is defined as the initial velocity, A is the acceleration, and S is the displacement. Now, how do we apply these for problems? Let's have a look. Here is a sample problem. We have a car which accelerates at 2.5 meters per second squared from rest for 10 seconds. Now, first off, the statement from rest is actually telling me that my initial speed u is equal to 0. Find the final velocity. The best way to tackle this problem would be just to simply write down SUVAT. So these are also known as the SUVAT equations for this common technique. Now, S is the displacement, U is the initial speed, V is the final speed, A is the acceleration, and T is the time. So let's make a list of everything that we know. Now, we don't know what the displacement is. However, we do know that the initial speed is 0. The final speed, this is what we are looking for. We know that the acceleration is 2.5 meters per second squared, and we know that this acceleration is acting on the car for 10 seconds. Now, all we need to do is look at these equations and see which one of those equations will be linking all 4 of these quantities. A quick inspection actually shows that the only equation that can link all 4 of these quantities is the first one, V is equal to U plus AT. So let's do that. V will be equal to U plus AT. We know that U is equal to 0 plus the acceleration, which is 2.5, multiplied by the time 10. So we know that our final speed V will be equal to 25 meters per second. Okay, let's have a go at a different example. So starting from rest, a car reaches 20 meters per second while it travels 500 meters. Find the acceleration of the car. Okay, so once again, from rest simply means that the initial speed is equal to 0. So I'm going to follow the same method. I'm going to write SUVAT over here, and we know that the displacement is 500 meters. We know that u is equal to 0, and the final speed, because it reaches 20 meters per second, will be 20 meters per second. The acceleration is what we're looking for. Okay, well, the only equation which links v, u, a and s is actually our second equation. V squared is equal to u squared plus 2as. So what I'm going to do is I'm going to use that equation, and I'm going to rearrange for the acceleration. So 2as is equal to v squared now minus u squared. However, remember u is equal to 0, so I'm just going to remove that term, and the acceleration will be equal to v squared over 2s. Now v squared will be 20 squared divided by 2 times 500, which is equal to 0.4 meters per second squared, and this is our answer for the acceleration. Okay, one more example. We have an airplane that has an acceleration of 3 meters per second squared, and starting from initial speed u is equal to 5 meters per second, reaches takeoff speed in 55 seconds. Find the displacement of the airplane from the moment it starts accelerating. Okay, so let's just write down SUVAT like so. We're looking for the displacement. And like so, we know that the initial speed is 5 meters per second, so it's probably just taxiing on the runway. And then we don't know the final speed. However, we know that the acceleration is 3 meters per second squared, and we know that the time is 55 seconds. Okay, so we need an equation that links S, U, A and T, and of course this is this equation here, S is equal to ut plus a half at squared. So I'm just going to write this down. S is equal to ut plus a half at squared. Okay, my initial speed u is 5 multiplied by 55, which is our time, plus a half times 3 multiplied by 55 squared. Remember, most common error in physics, or in A-level physics in particular, is just to miss out a square. So every time you see a square, please remember to not forget to square it. Okay, so putting that into a calculator, we're going to get up to two significant figures, about 4,800 meters, or about 4.8 kilometers. Okay, now let's have a look at some particularities of the equations of motion. First of all, if the acceleration is in the direction of motion, it is positive. If we have an object and we have some force acting on it or something like that, and it's being accelerated in this direction, and then the velocity is also in this direction and it's steadily growing under constant acceleration, then the acceleration is some positive number. If on the other hand we have an object which is moving this way, but maybe there is a frictional force which is acting in the opposite way and it's being decelerated, the acceleration is negative, then well, we take the acceleration to be a negative number. So I'm going to underline this. Some examples of this can include a car braking or an object being thrown upwards into the air. Now, talking about that, let's discuss falling under gravity. In other words, if an object is falling downwards, then the acceleration of that object is just g. So let's imagine this here is the Earth and we have this object, then its acceleration will be vertically downwards and it will be g is equal to plus 9.81 meters per second squared. Now, on the other hand though, and this is really interesting, if an object is being thrown upwards and it's slowing down, its velocity is decreasing, then we take the acceleration to be negative. So let's imagine that we have a ball and like we throw the ball upwards in the air, so it ends up here, it ends up here, and then it reaches some maximum height. So let's say this here is the maximum height. Like so, then the acceleration at all points is negative. So here g will be equal to minus 9.81 meters per second squared because it's acting in a direction which is opposite to the velocity. Okay, well, let's now have a look at a very typical problem. How can we determine the maximum height? So imagine I have this sphere over here and it's fired off at 5 meters per second. It will immediately start slowing down with deceleration or negative acceleration. G is equal to minus 9.81 meters per second squared. So we'll start slowing down and we'll reach some sort of a maximum height, let's say somewhere over here. So how do we know what is that maximum height? This is what we are trying to find out. Okay, well, let's use the SUVAT equations for that. So we're going to write down SUVAT like so. S, that's our maximum height. This is what we're looking for. So I'm going to write a question mark over here. U, this is the initial speed. This will be 5 meters per second. Now, something which is very, very critical, but at maximum height, our speed is equal to 0. Our velocity is equal to 0. So this is really, really important. So shall we just write this down over here? At max height, the velocity is equal to 0. You can imagine something kind of going up, slowing down, then the speed reaches 0, and then it starts accelerating again back down towards the Earth. Okay, well, we also know that the acceleration is minus 9.81 meters per second squared. Okay, well, we can actually use these SUVAT equations to determine the maximum height. I'm going to pick this equation, v squared is equal to u squared plus 2as. And what I'm also going to do is just rearrange that in a series of steps for s, the displacement. So 2as will be equal to v squared take away u squared. So our displacement s will be equal to v squared minus u squared over 2a. Now remember that in this case v is equal to 0, so the equation will actually be 0 minus u squared over 2a. Now u is 5 meters per second, so this will be minus 5 squared over 2 times the acceleration, which is minus 9.81. Because we're decelerating, the object is slowing down towards its maximum height. Notice that the two negative signs are going to cancel out, and we can just input this into a calculator and find the maximum height is 1.27. Let's use two significant figures, so this will be 1.3 meters. Okay, now let's have a look at an experiment to determine the gravitational acceleration in the lab. How do we actually know that g is equal to approximately 9.81 meters per second squared? Well, we're going to look at two ways of verifying this. One will be via just manual timing. What we're going to do is we're going to drop a marble from different heights and record the time it takes to reach the ground. We're going to measure the height h with a ruler. We're going to be measuring the time t with a simple stop clock. After we've done this, well, we're going to fill in our table of results, which will involve the height measured in meters, our time measured in seconds, and t squared, of course, measured in seconds squared. Remember, it's always good practice to have the units in any table of results. What I'm going to do then is I'm going to plot a graph of h against t squared. Now you may be wondering, why are we plotting a graph against t squared? Well, have a look at this equation. S is equal to ut plus a half at squared. This is one of the SUVAT equations that we've been looking at. Remember, u is equal to 0 because we're just dropping that marble with no initial speed. So we drop it from here and then the marble accelerates until it hits the floor. So s will be equal to then to a half at squared because this factor is 0. Okay, well, our displacement in this case is simply the height. Our acceleration will just be equal to g, and our time t squared, well, we've measured t and we've calculated t squared. So we can plot this graph of h against t squared. Now let's compare this with the equation of a straight line. So h is equal to a half gt squared. I'm going to add a plus 0. We're going to see why in a second. Right underneath this, I'm going to write y is equal to mx plus c. This is the equation of a straight line. We can see that if h is on the y-axis, if t squared is on the x-axis, the graph should be a straight line through the origin. So 0 is my intercept. It is 0. It goes through the origin. What's left for my gradient, m, is this expression, which is a half g. This is really, really important. So what I'm going to say here is that the gradient m is equal to a half g. So if we were to rearrange for g will be equal to twice the value of the gradient. Unfortunately, this method though is particularly prone to error. The reason for that is we are timing manually, and the average human reaction time is about just around a quarter of a second. After that, we're squaring this, which means that our percentage uncertainty will be getting larger and larger. So in order to reduce our uncertainty, we can do two things. So we can make sure that h, the height, is as large as possible. And once again, this is simply to reduce the percentage uncertainties. Another thing that we can do to reduce the uncertainty is use a contraption which is known as the trap door. So the ball is actually held via an electromagnet. So electromagnet. This is my artistic impression of an electromagnet. Should draw this in a slightly different color actually, just to show that it's magnetic. The electromagnet is connected to a trapdoor, like so. And shall I just color this in as well? So this over here is the trapdoor. And together they're actually connected to a timer. So just draw a little timer on the side, like so. Okay, so there's going to be some wires going in from the electromagnet and some wires going in from the trapdoor. Now, the timer will actually be able to determine the time between the ball falling down and the time it takes for it to set off the trapdoor. So it will give us a certain time, I don't know, let's say 0.52 seconds. And we can use a trapdoor and an electromagnet to reduce our percentage uncertainties. Now, yet another way to make our measurement of G more accurate would be to use light gates. Remember, we can use light gates to find the instantaneous velocity of a moving object. I'm going to use two light gates connected to a lab stand, and every time the object that we drop, for instance a marble, passes through a light gate, we'll know its speed. I'm going to use light gate number 1 to measure the initial velocity u. We're also going to be measuring the final velocity v using light gate number 2. We're going to measure the distance between them with a ruler. After that, we're going to use v squared is equal to u squared plus 2as. Our light gates are going to tell us what v and u are. And we're going to find the acceleration by simply rearranging v squared is equal to u squared plus 2as. As always, we're going to take multiple measurements and then find the average. Now, one more thing that potentially we can get asked on exams is proving the equations of motion. So let's have a look at some proofs of the SUVAT equations. Imagine that we have a v against t graph, so velocity against time, and we start from some initial velocity u. First off, the gradient of this graph will actually be equal to v minus u divided by t, because remember, assuming that we start off at t is equal to 0, the gradient is just change in y over change in x, and our change in y is just v minus u, where v, of course, is the final velocity. We can then just simply rearrange for v, and what I've done here is I've just brought the t over on the other side, and I get at is equal to v minus u. In other words, v is equal to u plus at, which is one of our SUVAT equations proved simply by using the gradient. Okay, well, let's have a look, or let's have a think about the area underneath this curve. We can actually think about this area, I shall just use a slightly different color, as the area of a trapezium. So this will be one side of the trapezium, this here will be another side of the trapezium, this here will be the height of the trapezium, like so. Well, the area of a trapezium is given by, let's see, a plus B, where A is one of the sides, B is the other of the sides, multiplied by the height of the trapezium. So you can imagine this is kind of a trapezium on its side, times h divided by 2. Well, hang on a minute. This is a velocity time graph. The area underneath a velocity time graph is the displacement. So S will be equal to U plus V, because remember the side A, this is just our initial velocity from 0 to here, is actually equal to U divided by 2, and V of course is the distance from here to here, which is equivalent to our side B, divided by 2 multiplied by the height, which in this case will actually be given by the time that's elapsed, which is t. Okay, so now we've derived two of the SUVAT equations. Let's see if we can crack the third one and derive that one as well. So let's think about this area once again. So I'm just going to focus on splitting it into two bits. First off, just this area here will be given by U times T. So the area of this, rectangle is just U times T. Now the area of this one will be equal to our base times the height, or half base times height, because that's the area of a triangle. So the area here will be a half times the base, which is going to be just t, and our height will be v minus u. So v minus u times t. Okay, well, the total area, which is actually our displacement, S, will be then equal to ut plus a half v minus u times t. However, remember, your acceleration is equal to v minus u over t. I actually have this written over here from our previous proof. So we could just use that equation, just rearrange that for v minus u. So v minus u will be equal to a times t. What I'm going to do is I'm going to take this expression, v minus u is equal to at, then I'm going to substitute that back into this equation. So then I'm going to get that s is equal to ut plus a half. Now rather than v minus u, I'm going to write a times t times t. Well, this of course is equal to ut plus a half at squared, and we've proved one more SUVAT equation. Okay, we're almost there. Let's prove the fourth equation as well. So let's start off with this one here. So S is equal to U plus V over 2 multiplied by T. Okay, well, remember, acceleration is change in speed, v minus u over t. Let's just rearrange the equation here on the right for t. So I'm going to say that t is equal to v minus u divided by a. Now what I'm going to do is I'm going to substitute that back into this equation here, and then we're going to get that s is equal to u plus v over 2. Now rather than t, I'm going to write v minus u over a. Okay, well, let's just do a little bit of tidying up in this fraction. So this is 2a, and we have s on this side. So I'm just going to essentially multiply both sides by 2a, or in other words, I'm going to bring the 2a onto the other side. So I'm going to have 2as is equal to u plus v times v minus u. Well, if we do the maths, this is actually equal to 2as is equal to v squared minus u squared. Let's rearrange that for v squared. So v squared will be equal to u squared plus 2as. And we've now proven the fourth SUVAT equation. So this is quite a lot of work that we've done actually. We started off here, we proved this one, we also proved this one with the area of a trapezium. Then we proved the last two equations by just being good at algebra and looking at the different connections. So hopefully you've enjoyed where do those equations actually come from. Okay guys, so now the final topic left for us to revise is actually stopping distance. So if we're in a vehicle, the stopping distance is defined as the sum of the thinking distance plus the braking distance. Now what do I mean by that? So imagine you are driving along, so let's just draw a little car over here, and you see some sort of a hazard on the road. It would take a little bit of time for the driver to react and to press on the brake pedal. So let's say half a second. During that half a second, the vehicle would have traveled some distance. We're going to call that distance thinking distance. Now, during that time, the car is just traveling at a constant velocity. So our thinking distance, so I've called that just S subscript thinking, will just be equal to the velocity of the car. Let's give that U multiplied by the thinking time. Let's just call that T. Now, as soon as we reach this point, the driver now presses the brake pedal and the car starts to decelerate. So let's say that here is the braking point. So at this point, we actually press the brake pedal. Now, in this case, now we're going to have some negative acceleration. So to calculate the braking distance, I'm just going to call that S subscript B just for the purposes of this video. So I'm going to use the equation V squared is equal to U squared plus 2AS. Now rather than S, I'm going to write S subscript B just to show that this is the braking distance. Okay, well, our final speed was going to be equal to 0 because the car will stop. So V will be equal to 0. So we can say that 0 is going to equal to U squared plus 2AS. And we can just rearrange for our braking distance, which is simply going to be minus U squared over 2A. Now note that the acceleration will be negative. So let's just say that A is negative. So A is negative, and this would mean that your displacement will be positive, your braking distance will be positive, because this minus sign will get cancelled out by another minus sign, because the acceleration is indeed going to be negative, because the car is slowing down. So we can use this formula to calculate our braking distance. So remember our thinking distance, two very important formulas. Thinking distance is just speed times time, U times T or V times T, and our braking distance is minus U squared over 2A. Now this is a formula which is not given in the exam, but we can always derive it really quickly using the equation that V squared is equal to U squared plus 2AS. Remember, our stopping distance is defined as the sum of those, so let's just write this down underneath here, that our stopping distance, I'm just going to call that S, let's give it a subscript. So our stopping distance is just going to equal our initial speed, let's just say that this will be equal to the thinking distance, which is our initial speed times time, plus our braking distance. Okay, well now what are some factors that affect each of those? So for our thinking distance, well, this is all about the condition of the driver. So for instance, if they are under the influence of alcohol or drugs or tiredness, this will actually increase the thinking time. This will increase the thinking time, and thus, because they're directly proportional, it will increase the thinking distance. Now, the braking distance will be all about the actual value of the acceleration that your car or your road can provide you. So this will be dependent on the conditions of the tires, for instance, so conditions of the tires. It will also be dependent on the mass, so let's be precise, the mass of the vehicle. Because if, let's say if you have a lorry that has been loaded, an equal amount of force braking force will produce less of a deceleration if the mass of the vehicle is quite high. Also, the conditions of the road will have an effect. So for instance, if it's wet or slippery, then our braking distance will increase considerably. One final thing I would like to mention, and we'll also explain why there's so much energy unfortunately involved in car collisions and why you should all be super careful on the road, is just energy. So the kinetic energy of any vehicle is given by a half mv squared. So this means if my velocity increases by a factor of 2, so this becomes 2v squared, then my kinetic energy will actually be 4 times that amount, because 2 times 2 squared is, well, 4, so this will be equal to 4 times a half mv squared. So if we were doubling our speed, we're actually quadrupling the kinetic energy. Additionally, if our braking time, let's say if our speed increases a little bit, then our braking distance will increase by this factor squared. So let's say that we have our initial speed to be 2u, then our braking distance will essentially be increasing by a factor of 4, because we just get a factor of 4u squared, because it's 2 squared over 2a. So this means that if I increase my speed, if I'm driving twice as fast, my distance will not increase by the same factor, but will increase by that factor squared. So my braking distance will be 4 times as much. So something to be really, really mindful about. Okay, folks, well, we've actually covered pretty much everything of motion. Thank you very much for watching. Once again, if you're looking for projectile motion, I have a fully separate video for this. Thanks again for watching, and I'll see you in the next video.